You know when you see those headlines about a new medical breakthrough? Well, behind every single one of them, there's this hidden number. And that number is the difference between a study being a true game changer and, well, just statistical noise. Today, we're demystifying that number.
It seems like such a simple question, right? But the consequences are huge. I mean, if you get this number wrong, a really promising new drug could get tossed aside, or worse, a totally useless one could get celebrated. So you see, it's not just about getting big numbers, it's all about getting the right number.
It's basically the Goldilocks problem of medical research. If you go too small with your study, your results might just be a total fluke, completely meaningless. But if you go too big, you're just burning through time, money, and this is a big one, you could be putting people at risk for no good reason. The whole goal is to find the size that's just right.
So, okay, how in the world do researchers land on this magic number? Well, it's not just a guess they pull out of thin air. It's actually a lot more like a recipe. And just like any good recipe, it all starts with a few key ingredients. So let's take a look at what actually goes into the mix.
All right, first up on our ingredient list is something called effect size. And put simply, this just means how big of a deal is the thing you're looking for. Are we talking about a massive, can't miss it kind of improvement? Or is it something really small and subtle?
I love this analogy. It really boils down to this. Are you looking for a brick in a haystack or a needle? If the effect you're looking for is huge and obvious, like that brick, you probably don't need a huge sample to find it. But if you're trying to find that tiny, subtle effect, that needle, well, you're going to need a much bigger haystack to sift through, just to be sure you don't miss it. Okay, let's put some real numbers to this. Imagine a standard drug lowers a patient's blood sugar to, say, 140, but you've developed a new drug and you think it can get that number all the way down to 120. That 20-point drop? That is your effect size. That's the specific needle your entire study is designed to find.
Okay, our next ingredient is all about managing risk. Because, studies can be wrong, and they can be wrong in two main ways. First, you have what's called a type 1 error, which is basically a false alarm. The study finds an effect that isn't really there. Then there's the type 2 error, which is a missed discovery. There actually is an effect, but your study wasn't powerful enough to find it.
And that idea of a missed discovery leads us right to our next ingredient, a study's power. You can think of power as its confidence level. It's the study's ability to actually find a real effect, if one truly exists. Researchers will usually set the power at something like 80 or 90%. What they're really saying is, hey, if there's something real here to find, we are 80 or 90% sure our study is strong enough to detect it. Basically, high power means you're not going to miss something important. Okay, so let's recap. We've got our ingredients, the effect size we're hunting for, how much error we're willing to accept, and the power we need to be confident. Now for the fun part. Let's see how researchers mix all this together because believe it or not, the recipe actually changes depending on what kind of study they're doing. Now, I'm going to show you something that might look a little scary. Researchers use formulas that, can look pretty intense, but, and this is the important part, you absolutely do not need to be a math genius to get the big idea here. The logic behind it is actually surprisingly simple. It pretty much boils down to three simple steps, and this is true for all sorts of studies, whether it's a big survey or a head-to-head comparison of two drugs. Step 1, you figure out exactly what you're trying to measure. Step 2, you just plug in your ingredients, your effect size, your power, all that stuff. And then step 3, you let the formula work its magic and spit out that number. All right, theory is great, but let's see how this plays out in the real world. Let's imagine a team of researchers is testing a brand new drug for urinary tract infections. And they're going to use the gold standard for this kind of thing, a randomized controlled trial, or RCT. Okay, so here's what they know. The current standard drug, it has about a 65% recovery rate. Not bad, but they're hoping their new drug can push that all the way up to 85%. That gap, that 20-point difference, that's their effect size. That's the prize they're hoping to find. So they go to their formula. They plug in all the ingredients. That 20% effect size they're aiming for, they set a really low risk for a false alarm, and they give it a solid 80% power so they don't miss a real effect. They run the numbers, and what does the recipe call for? 140. That's it. 140 participants. You give 70 the new drug, 70 the old one. That is their just right Goldilocks number. Okay, so that all sounds pretty neat and tidy, right? But we all know the real world is a lot messier than that. Research definitely doesn't happen in some perfect mathematical bubble.
There are always real-world complications you have to plan for, even after you've got that initial number. And probably the single biggest complication is something called the dropout rate. You see, people aren't lab rats. They have lives. They move away, they get sick with something else, or they just change their minds and decide to leave the study. And researchers absolutely have to plan for this.
So think about it like this. Let's say your magic formula told you that you need 80 people to finish your study to get reliable results. Key word there is finish. But you're an experienced researcher, and you know that realistically, about 20% of the people who start probably won't make it to the end.
So what do? Well, you have to do some simple math and work backwards. If you need 80 people at the finish line and you expect to lose 20% along the way, you actually need to start with 100 people. You have to over-recruit just to make sure you have enough data at the very end.
And here's the thing, dropouts are just one part of it. There are a ton of other practical things that can change that number. Like, do you actually have the money and the staff to run a giant trial? Because a huge sample is pointless if you can't manage it. Or what if you want to look at different groups separately, like men versus women? Well, you might need a bigger overall sample to get good data for each of those subgroups. All of these practical questions have to be answered. Okay, so after all of that, all the ingredients, the formulas, the real-world problems, you might be asking, why? Why go through all this trouble? Why is this one number such a big deal?
Well, it's because getting this number right is pretty much everything. It's what separates real, reliable science from just random chance. It makes sure we're not wasting precious resources, time, money, and the effort of volunteers. But honestly, the most important reason is ethics. It's an ethical must-have. Researchers have a responsibility to make sure they aren't exposing one person more than is absolutely necessary to potential risks.
But just when you think you have it all figured out, here's one last fascinating little twist for you. For all this talk about big, carefully calculated trials, it turns out that a lot of the most famous Nobel Prize-winning discoveries in history actually came from studies with really, really small samples. And that leaves us with a really interesting question to chew on, doesn't it? When you're trying to prove a treatment works, getting that sample size just right is critical. But maybe for those once-in-a-generation revolutionary breakthroughs, it's not about the size of the sample, but the depth of the investigation. It's a great reminder that when you're on the cutting edge of science, bigger isn't always better.